Hello students, how are you? My name is Todd Yurchisin and I'm the instructor for PSE 2121, Fundamentals of Physical Science. And of course this class is about teaching some general physical science principles, and in this class, my particular class, I'm using astronomy as the background. What we're going to do today is talk about electromagnetic radiation and light waves, and because when we look up into space, when we look at these objects out in space, that's what we can see, that's what we can detect. We have telescopes to see, we have optical telescopes to see visible light, but we also have many other telescopes that can look at radio waves and gamma rays and such, so we can see the whole spectrum now. And of course that comes with the fact we've had advances in technology. Originally we could only see with optical telescopes, but now we've invented things to detect other waves of electromagnetic radiation. So let's do some basic, some definitions with electromagnetic radiation. It's a form of energy. It travels through space at the speed of light, and for our class, we're just going to use the number 3 × 10⁸ meters per second. So just write that down and just ingrain that in your brain, as that's the number we're going to use. The speed of light is 3 × 10⁸ meters per second. It's an oscillating wave. Light travels, it's considered, they call it a wave and a particle phenomena. In other words, we can do experiments that show that it acts like a wave. We can also do experiments to show that it acts like a particle. And historically, the guys that were looking at this kind of thing, they would argue back and forth. It's a wave. No, it's a particle. It's acting like a wave. No, it's a particle. And the bottom line is we still haven't resolved that, and because it's something that's so small that it could act as both. So in other words, what we say today is that we can do experiments to show one and do experiments to show that it acts like a particle. It's a regenerating co-oscillation of mutually perpendicular electric and magnetic fields. I know that's a mouthful and it doesn't really matter, but the wave, we have a magnetic field and a electric field, and they're mutually perpendicular and they're oscillating back and forth. And I have animation here showing, you can see they've placed a card at one end here, and as the wave moves along you can see that the electric wave is increasing and the magnetic wave is increasing and then decreases to 0. So now that I've shown you that, I'm just going to draw one wave from now on. I don't really need the two waves, and we don't really need to concern ourselves with that part of it. So we need to define some characteristics of waves. And so the definition of a wavelength is, here I have a wave, and I'm measuring the wavelength, the length of the wave. It's right there in the word. What is the wavelength? It's the length of the wave. And I'm measuring, this is any wave by the way, I'm measuring from, in this case, the crest to the crest of a wave. It doesn't matter where we measure it from, as long as it's a corresponding point to the wave. We can measure from this point to this point. That is a wavelength from there to there. You can see that the wave is descending along the equilibrium point, and here it's descending along the equilibrium point, across the equilibrium point here. So that is a wavelength. And from trough to trough would be one wavelength. So a wavelength is the distance between two corresponding points in the wave. Over here, wavelength, we're going to use the symbol of lambda. The lambda, in this case, it's drawn a little more stylistically like this. And this happens to be a small Greek letter L. And it's L for length. So that's what we use. We don't use L because that's being used somewhere else in science. And typically the world over, when you see this symbol, they usually mean wavelength. So in any language, that's what it usually means. So, and since it's a length, it's in units of length. In our units, we use meters in our class. We use meters. The next one that we need to know is about frequency. Frequency is a measure of the number of wave cycles that move through a point in space, and in this case, 1 second. Frequency is how many waves pass a point in a certain amount of time. For our purposes, it's a second. You can see that here I have a longer wave, and here I have a shorter wave. The longer wave, these are both traveling at the same speed, and for our class, they're both traveling at the speed of light. If they're both traveling at the speed of light, this one with the longer waves, how many waves are going to pass a certain point in 1 second? Well, not very many of them, because the wave is longer. If the wave is a lot shorter, then this will pass a point, a lot more of them will pass a certain point in the same amount of time. So the frequency is how many waves pass a point in 1 second. So, and I just showed you that if it's a longer wave, if it's a bigger wave, a larger wave, then it has a smaller frequency. And if it has a shorter wave, then it has a greater frequency. So they must be related somehow. And they're related by the fact that their product, the wavelength times the frequency, their product is, we're talking about electromagnetic waves, their product is the speed of light. So this is one of your first formulas, the speed of light. Speed of light for our class is 3 times 10 to the 8th meters per second. And wavelength is going to be in meters, and frequency is in hertz or 1/seconds. So you can see that if I multiply, let's look at the units. C is a speed, and it's going to be in meters per second. And that is wavelength times frequency. Wavelength is in meters, and frequency is expressed in 1/seconds. You can see that we're going to end up with meters per second. Remember, students, I keep telling you, watch your units. Keep track of your units, because that's going to make sure that you have the right scale of everything. So here's the electromagnetic spectrum. And on the top here we have wavelength, and you can see that down here we have very long wavelengths. The wavelength here is 10 to the 12th nanometers, which is about a kilometer long. So you can see that the wavelengths are very large, and it decreases as we go up the electromagnetic spectrum. And conversely, on the other side we have frequency. When the wavelength is very long, we have a very low frequency, and the frequency continues to go up as we go further along from radios to microwave, infrared, visible, ultraviolet, X-ray, and gamma. And yes, I want you to know that order. I want you to be able, there's a question on the test that will say which order do these go in. Please pick the one that shows the order of the different kinds based on, say, from shortest to longest wavelength, from longest to shortest wavelength, or from highest to lowest frequency, or lowest to highest frequency. I can ask that question 4 different ways. In fact, I probably do. I probably ask this 2 questions with wavelength and frequency, and then different combinations of that. So, quick review. Which has the greater frequency, the red light or the green light? Well, the green light has the greater frequency, because the wavelengths are smaller. More of them will pass through a point than in any given time, than in 1 second, than will the red. Which one has the greater wavelength? Well, clearly the red light has greater wavelength, and you need to know that. You need to remember that red light has a longer wavelength, and therefore a lower frequency than does the blue than does blue light. So let's talk about now the wave versus the particle nature of light. In 1900, Max Planck proposed that radiant energy is not continuous but is emitted in small bundles. This is the quantum concept. No, I'm not going to ask you about Max Planck and what year and all that stuff. I just want you to understand what the quantum concept is. Radiant energy has both, as I said before, has both a wave nature and a particle nature. And we can do experiments that show that it can act both ways. An individual unit of light, then, a packet of light, we call that a photon, probably something you've heard. So the quantum concept says that energy is present in small, discrete bundles. For example, a tennis ball that rolls down a ramp loses potential energy continuously. What's potential energy? Well, if it's on the ground, it doesn't really have any energy compared to relative to the ground. If I pick it up and put it at the top of the thing, and if it were to fall on something, it could break it or something. Where'd the energy come from? It's potential energy because I put it up there. And that's what I mean by potential energy in this case. Put the tennis ball up here. If it rolls down the ramp, it's losing this potential energy continuously. As it goes from one small step to the next, it's losing just a little teeny bit of energy. However, the quantum concept says that no, it has to lose this amount of energy. A tennis ball that's rolling down stairs loses the potential energy in steps, literally. When it falls down one step, it's lost that amount of energy, and then it hasn't lost any more. In other words, and it can't stop halfway through. It either loses all of it or none of it. And that's what we mean by quantized energy. The loss is quantized. So keep that in mind as we go to the next bit. Niels Bohr, came up with the idea of electrons and orbiting or spinning around, or rather energy levels in an atom. And he said that electrons only exist in certain allowed orbits. So, in other words, here is the nucleus of an atom, and here is my first energy level. Here is another one after that, and here's another one after that if it exists. Actually, the energy levels are there always, they just aren't necessarily being used. Within the orbit, the electron does not radiate. As the electron is in this energy level, it doesn't radiate or absorb. It doesn't give off energy. It's just happy in that energy level. Radiation is emitted or absorbed when changing orbits. If this were to be pushed up, if I were to put energy from outside and push this electron up to this energy level, it has to absorb a certain amount of energy, a quantized amount of energy, a specific amount. And if it were to, say, be pushed up to this orbit here, it doesn't want to stay there. Nature wants it wants to fall back down again. It went up there because we put energy into it. And it will fall back down again, and it will give off a certain amount of energy, that exact same amount. And in other words, if I put in half that amount of energy, it's not going anywhere. The energy, it's not going to go up halfway. It's going to go up here or stay there. It's not going to go any further. I can also put energy in that will push it up to here. How much energy does it take? It takes this amount. If I have 3/4 of it, I'm not going anywhere. Actually, it might push it up to this level, and then you got some leftover that goes into the kinetic energy of the molecule itself. So what does this mean for us? Well, it means that this is how we see light. Light is when this electron falls back down again, you can see that this isn't a lot of energy here. This isn't a lot of energy. But we quantify this by, this is Planck's equation here. E equals hf. What is this? This is the energy that it takes to do this. Energy of the photon. This is the amount of energy it's either absorbing or giving off when it's going from one level to another. And when it drops back down, the amount of energy it gives off is related to the frequency. This is f, this is the frequency. And this is Planck's constant. Don't worry about it, it's just a number. I will give that to you. Planck's constant, I'm going to give that to you. Don't worry about it, it will be there for you to use. It's just a number. What I'm trying to say here is you can see that the amount of energy it gives off is directly proportional to the frequency it's going to give off. So, in other words, when this electron falls from here to here, it gives off a relatively low amount compared to this, and so it might be a long wave red one. It could be. And then this one, when this one drops back down, you can see that this is a lot more energy coming from here. So this amount of energy here would be greater. This is a greater amount of energy. So the energy is larger. Therefore, remember this is a constant. Therefore, this must be bigger. So the frequency of this light, it could be a shorter blue wave coming from there. And this is how we see light. So, when an electrical voltage is passed through a gas in a sealed tube, a series of narrow lines is seen on a spectrograph. The lights in this room, the fluorescent lights, look at a fluorescent bulb. At either end is an electrode. We're passing very high voltage through here. Energy is jumping across here through the gas. The gas is absorbing some of this energy. And the molecules in there, possibly mercury vapor, some of the energy is going into raising electron up to this level. Some of it goes into raising to this level. Some of it perhaps even higher. As the electrons do not want to stay there. They want to fall back down again. As they fall back down again, they give off the same amount of energy. Remember, the energy coming in is electrical energy. The energy being given off as it falls back down again is released as a frequency of light. And that's why we have light. That's where the light's coming from. So the fluorescent bulbs, the lights in this room, That's what's happening. So, and these different, if we were to take that light and run it through a prism, a spectrograph, we will see different lines of different colors based on from where the electron fell. And we call this an emission line spectrum. How are you going to remember this? I'm going to show you in a little bit. It's an emission line. Well, it's right there in the definition. Emission. It's being emitted. Light is being emitted. So the evidence that we have for this, here's a electron coming down from level 3 down to 2. You can see that that's a certain amount of energy, and they've colored it red because it's not a lot. And remember, red is a longer wavelength, and you can see that so if it's not as much energy, the frequency is lower, and a lower frequency of light is red. And then here, this one is dropping down from level 4 to 2. So from level 4 to 2, it's even greater amount of energy than the other one was. And in this case, it's the blue-green one. I believe this is hydrogen, by the way, that we're talking about in this case. And then you have one that drops from level 5 to 2, and that's this one, and it's colored violet. And then there's another one from 6 to 2, and it's even higher energy, and it would be further over in the violet here. It's not on the screen here. So the red line is the least energetic and corresponds to an energy electron. This is the least one, dropping from an energy level of 3 down to 2. So what does all this mean for us? It means that when we look at an electromagnetic spectrum, we can tell exactly what material this is. We know what this is. More on this in a bit. So the photon energy, I gave you this equation just a few moments ago. The photon energy, this is the energy of one photon. How much energy this photon has being given off, how much that has, is based on the frequency of its radiation. So photon energy E, F is the frequency. Here is Planck's constant. This is what you can use, 6.63 times 10 to the negative 34th joule seconds. That is a joule second. Let me show you that part of it. If we have energy equals, and this is in joule seconds, and frequencies in what? It's 1 over seconds, isn't it? Multiply that out looking at the units. The seconds cancel out, and this is in joules. Now, perhaps none of you have ever heard of the term joules, but it is a unit of energy. It's a unit of energy, so it works out. Don't concern too much about that. Just tell me when we work the problem, just tell me that it's joules. So this number here is a constant. You're going to use that over and over again. And you can see now that the energy of the photon, quick review here, the energy of the photon is proportional to its frequency. So what does that tell us? Here is the frequency. Remember, down here with long radio waves, the waves are very long. They're very long, which means what? Based on the fact that the speed of light is proportional to its frequency. The speed of light, the speed of light is constant. The wavelength is proportional to the frequency. Sorry about that. That the longer the wavelength, the smaller the frequency, because their product has to be is a constant. So that tells us with longer radio waves, the frequency is relatively low. As we go up in the spectrum and the wavelengths get shorter and shorter, the frequency gets higher and higher. All you got to do is take this frequency getting higher and higher. If this is going up, we're multiplying it by just any old number. It's just a number. That means the energy goes up. In other words, as we go from radio waves on up through infrared, ultraviolet, X-rays, and gamma, these are becoming more and more energetic. For over 100 years now, we've been bombarded by long radio waves. We've been broadcasting radio for some time now, and television and such. It doesn't seem to hurt us. Not really sure about that, but in general, it doesn't seem to be bothering us. What you don't need, by the way, this is not a class in radio transmission. This is not a broadcasting class. So the fact that it's got AM here and FM, that's just designated by the FCC. Don't worry about that. We don't care about that. All I want you to know is that down here with the longer waves, these are radio waves. Then we go into microwaves. Microwaves are, you probably have one of these at home. Put something in the microwave oven, turn it on, and cook something. And by the way, the mechanism of cooking is that it's it's cooking at a frequency that excites water molecules. It makes water molecules move faster. So when you're cooking something in the microwave, essentially you're making the water molecules move faster. When that happens, it's heating up. The faster the molecules move, we see that on our level as heat. So microwaves are even more energetic than radio waves. Beyond that, we go into infrared. And I don't want you to mistake the fact that infrared, they're more energetic. Infrared waves are more energetic, and yet we have infrared. Some waves don't cook, and yet the microwaves do. I thought they were more powerful. That has to do with intensity, how many waves are doing this, and I'll get to that in a little bit. So don't confuse that part of it. And then above that becomes visible. You can see that right next to infrared is red light. So infrared, what does infra mean? It means below. So these waves are just below red. As we go through the rainbow of colors, we go from red to orange to yellow to green, blue, and then violet. Beyond that, just above visible light, this is what we see. And the next one above that is ultraviolet. It's called ultraviolet because what does ultra mean? It means above violet, so these waves are above violet. Beyond that, we have X-rays and gamma rays. So we've been bombarded by radio waves for a very long time. Doesn't seem to hurt us. Microwaves, if you're standing out at the airport, you're being hit by microwaves because the radar's hitting you. You don't want to get inside of a microwave oven, of course, because that could cause some problems. But that has to do with more the fact that there are a lot of them. There are more of them. Our cell phones use microwaves, and we're being bombarded with microwaves, but those are relatively low intensity. Above that, infrared rays. You've seen perhaps at a restaurant. I usually think of IHOP, International House of Pancakes or something, and this is what I usually think of. And you've ordered your pancakes, and they put your breakfast up on a little shelf there, and the guy rings the bell, and the waitress comes running over there, and she picks up the platters from the back of the kitchen, and there's some lamps sitting there above the food. There's probably some red lamps there, and it's keeping your food warm, and those are infrared lamps. If you've ever been up north in a hotel or something, and it's cold outside, and you get out of the shower, and they usually have a switch, and they have infrared lamps in the bathroom. You just turn it on and keep you warm while you're drying off. So, and infrared rays, so you don't really want to get hit by too many of those. And we have visible light. Ultraviolet rays, that's the stuff where we have to put the cream on. You don't want to get hit by too many of those. Why? Remember, these are getting more and more energetic here. So we put the cream on so we don't get sunburned, because we start getting hit by a lot of those, we're going to end up getting burnt. X-rays, you don't want too many of those in your lifetime. When you go to the dentist, what do? When you go to the dentist, they put that lead thing on your body, you know. They put that thing, you're laying there, and they put the thing over there so it goes all the way down your body here so they protect you so you can still have kids when you get older. And they leave the room. They don't want to get bombarded by these X-rays. Rather dangerous stuff to get too many of those in your life. And gamma rays, it would be best not to get exposed to any of those at all, if you can help it. There's a certain limit that you have in your lifetime. You don't want any more than that. So what we're going to do is the speed of light, this is our other equation, the speed of light equals the product of the frequency and the wavelength. So let's play with these a little bit. Light exists as both waves and particles, or packets of light called photons. Characteristics of waves, quick review here. There's the frequency and the wavelength, and their product is the speed of light. Characteristics of photons, the energy of a photon is directly proportional to the frequency. In other words, the energy of the photon is directly proportional to frequency. You can see that if this goes up, this has to go up. Remember, H is your constant of proportionality. We talked about proportionalities. So when this goes up, and we showed that on the previous slide. It's inversely proportional to the wavelength, because if it goes up with the frequency, it must go down with the wavelength. And here's Planck's constant. Remember, you have these slides in your possession. You can go back over and look at these. So let's take these two equations, and using algebra, we can manipulate these two equations several ways. For this, and you're going to have a homework problem like this, we can solve for lambda. We can solve for the wavelength. I'm going to ask a question on the homework. Given this frequency, what's its wavelength? Well, all you got to do is take this equation and solve for the wavelength and plug in the numbers, and you'll have the wavelength. Same for the frequency. You can you can solve for frequency. So frequency then, if you solve for it, is c over lambda. And we can plug that into the other equation, E equals hf. So here is energy of the photon equals Planck's constant times the frequency, and the speed of light equals the product of wavelength and frequency. Let's solve for frequency here. Frequency is speed of light over the wavelength, and let's put it back into here. The energy of the photon is Planck's constant times c over lambda. Better written, hc over lambda, okay? So now you can see, using what I was showing you about direct and indirect proportionalities, the energy of the photon is indirectly proportional to the wavelength. You can see it's when you're dividing on the bottom here. So if this goes up, if this gets larger and larger, that means when we divide this larger and larger number into these two numbers, which is a constant. Hc is a constant. It's just a number. When we take this number and divide it by a bigger and bigger number, this number here gets smaller, which is consistent. In other words, the longer the wavelength, the lower the energy that it has. Let's talk about this Hc for a second. This is sort of a sideline here, because this is a product of two constants. It's just a number. By the way, here's another one of your things here. It's just a number. Well, what is H? H is 6.63 times 10 to the negative 34 joule seconds. And 6.63, just follow along here with me, because we're going to make this a lot easier so that you can just use one number, because this is just a number, and I'm going to be asking you to use this. 6.63 is nearly 6.67. What is 6.67? It's 6 2/3. All right? And we're going to multiply this by the speed of light, 3 times 10 to the 8th. So we're going to multiply 6 2/3 times 3. Well, 6 2/3 times 3 is 20. Simple enough. Pull out your calculator, multiply this times the speed of light, you'll get 19.85. All right? Hey, 20 is close enough. Just use 20. So for Hc, you can use, and this is not scientific notation, but that's okay, because, well, you'll see in a second. So for Hc, the product, you can use 20 times 10 to the, remember in lab, we worked with powers and such. So when we multiply 10 to the negative 34th, 10 to the negative 34 times speed of light, which is 10 to the 8th, 3 times 10 to the 8th. When we multiply these two numbers here, what do we get? We get 10 to the negative 26. So you can, for Hc, you can use 20 times 10 to the negative 26. And let's look at the units real fast on that, everybody. Remember, the H is in joule seconds, and we're multiplying this by the speed of light, which is meters per second. Seconds will go away, and you have a joule meter. Now, what the heck is 20 times 10 to the negative 26 joule meters? It doesn't matter. It's just a number that we're going to multiply and use. It's a proportionality constant. Use this number. You don't have to, and I know half of you won't. Most of you will still plug in the calculator and get 19.85, but you're going to end up with numbers like 4.98 or something like that when I'm looking for a 5, which is fine. I'm just saying that it's a lot easier this way. You don't have to do it this way, but it's just a lot easier. I've just combined the two numbers because it's much easier to use it this way. So now, am I going to ask a question like this? Yeah. On my homework, I've got a thing where I'm giving you the wavelength of the light. Tell me the energy of the photon. So you have to either make this substitution or find what the frequency is. A lot of students will do that. They'll do this first, do the frequency, and then plug it into there. Well, that's a lot of writing. Just combine the equations first and then go from there. Here's an example. If the wavelength of a microwave beam is 11.5 centimeters, then what are the frequency of the radiation and the energy? The frequency is, first convert to meters. We need to convert the meters of we need to convert centimeters into meters. Why? Because our speed of light is in meters. So we want the frequency and we're using C equals lambda f, I've got the wavelength. So the frequency is C over lambda. C is 3 times 10 to the 8th meters per second, divided by, and this was 11.5 centimeters. We need to convert the centimeters to meters, everybody. Remember to do that. Remember to do this in the test. And by the way, remember what I said. If you don't do this, that answer is on the test. The wrong answer is on the test sitting there waiting for you if you didn't do this. So let's put in the conversion factor. We have 100 centimeters per meter. See how I wrote that? Remember this? We did this in class. I put centimeters on the bottom. I wanted it to go away. I put it on the bottom. I now have meters here. Let's look at our units. On the top, I have meters per second, and I'm dividing it by a meter. If you may recall, meters per second. When you divide something by something, you multiply by the reciprocal. Meters goes out. What I have left is 1 over seconds. Is that a unit of frequency? Yes. So our units work out. So now all we have to do is this mathematics. If I'm dividing in the bottom here, if I'm dividing by 100 down here, then actually I'm multiplying by 100 on the top. I can bring this on top. So 3 times 10 to the 8th times 100 over 11.5 is what you're going to shove into your calculator, whatever that is. And it comes up to be 2.6. 2.6 times 10 to the 11th inverse seconds. So that's what our frequency is. Then we can, if we want to, we can take that and put that into our energy equation. But another way to do it is E equals hc over lambda. We can take this and do, here's h, 20 times 10 to the negative 26, this hc, joule meters. Divide that by 11.5 centimeters. Let me just go ahead and divide that by 100, because this is now in meters. So look at our units. Meters goes out. I have joules left over. Is that a unit of energy? Yes, it is. Do that multiplication, and you'll find out how much energy that photon has of a wavelength of 11.5 centimeters. Hopefully you follow that. I'm going to do examples in class like this again. And yes, it's on the homework, and yes, it's on the test. So back to the energy levels falling down as electrons fall down from one energy level to the next. It's characteristic of atoms. In other words, mercury has one set of light that it gives off, and others. Helium has this pattern. So if we were to pass electric energy through a gas filled with helium, it's going to emit these frequencies and these bits of light on an emission line spectrum. So, and here's lithium and sodium, and here's mercury. So that means that when we see this pattern, we know what element it is. What does that mean for us in astronomy? Well, we can look at the light of a star, and we can tell what it's made of. We can tell very many things about it, and knowing what it's made of tells us quite a bit about its size, its age, and etc. So that's how it's useful. So in other words, we could look at these stars, and they're many light years away, and yet we can tell quite a bit about them. And more about this in the next unit. But this is one of the tools that we use. Again, backing up, this is our general physical principles, some background information that you're getting here in order to use this. So this is how we explore space when we look out there. So we can pass, here's neon. Neon light is a reddish color. And we have neon in these tubes, and electrical energy is being passed in it. And it's mostly reddish color. It passes through a prism, and it breaks up. And so here's neon on the bottom. If you notice, why does it look red to us when we look at neon? It looks red to us. Yes, there's a lot of red lines here, but there's also some green and some blue and such. When you take all these colors, a continuous spectrum has all of these colors in it, and that's pure white light. All of the colors are in it. When they mix together, you get white light. When we look at neon, we see mostly red. Well, why do we see mostly red? Why don't we see a whitish color? Because we've got some green and some blue and such. Well, let me digress once again and talk about intensity. Intensity, strictly speaking, the intensity of light is the power of the light over a certain area. In other words, here I have, let's say, 1 square meter. And I've got a bunch of light waves hitting it. Here I've got some light waves hitting it. Intensity, if I only have a few light waves hitting this area here, it's not going to be very bright, because that's what you think of as intensity. It's not going to be very bright. And this power here, this I equals PA, I equals power over the area. What is power? Power is just how much energy per unit of time. Don't worry too much about it. What energy is this? Well, this is that E equals HF, because that's what we're seeing here. We're seeing the frequency of light here. We're seeing the frequency of light on this square meter. So the power here, and this is per unit of time. It doesn't matter. Don't worry about that. It's per second. And then it's over a square meter. Don't get too confused about quite a bit of this here. What I'm pointing out, what I'm trying to say is that intensity is we're measuring how much power of the light is hitting this certain square meter. What is power? It's energy per unit of time. So every second we have this much energy hitting it. What is the energy? The energy is this light, HF. And this energy here equals HF. This is the energy of 1 photon at that particular frequency. So if we have, here is the energy of 1 photon. What's the energy of 2 of them? What if I had 2 of these? What's the energy? The energy of 2 of these photons is going to be twice as much, right? And if I have 10 of them, the energy of 10 of these is going to be 10 times that amount, isn't it? So what's the measure? What is the energy of a lot of them? An n number of them, a large number. It's going to be an n number times times Planck's constant times the frequency of that 1 photon. What I'm getting to is that means that this power here over this area, the amount of energy hitting it, really what we're measuring is how many waves are hitting this square meter. Because if one of them has this energy, and we've got a bunch of energy hitting it, that must mean that it's made up of a bunch of waves. So intensity then is, essentially, you're counting up how many waves are hitting this area. That's what I mean. So now back to this. If neon lights look reddish to us, and yet it gives off a spectrum that has blue and green in it, when we mix those together, why doesn't it appear more white? It's because when you look at this, we're going to do this in a lab, by the way. When you look at these are brighter. These are more intense. There are more of them. There are more light waves of these. These are dimmer. They will appear literally dimmer because they're not as intense. There's not as many of them. So these, the reddish and the yellows, they overcome and wash out these. So when you mix them together, that's why you see a reddish color instead of a whitish color, even though it has all those other frequencies in there. All right, Kirchhoff's laws. So what's a law again? We talked about what a law is. What is a law? It is a relationship that we observe in nature that we see over and over again. And if we think of what we're seeing in these terms, in this mathematical terms, then it works. Every time we do it, it works. Kirchhoff's law says this, that you get a continuous spectrum if it's a solid or liquid body radiates in an interrupted, if it's solid or liquid. If we have something that's very hot and it's very dense, so continuous spectrum comes from a hot, dense. Those are the 2 words I will be looking for on a test if it should come up. It's a hot, dense object. It's continuous. Well, why doesn't it radiate in lines? It's because this object, yes, it's made up of certain molecules and it should be giving off certain frequencies like we saw before. It's made up of particular things and it should be giving us the characteristic signature of what it is that it's made up of. However, what's happening is because it's solid, the molecules are so much closer together and they're knocking against each other and they're creating waves of their own that have nothing to do with the electrons falling up and down. So the denser an object is, then the more you're going to see more of a continuous spectrum from that object. An absorption spectrum is exactly that. It's right there in the word, absorption. If you have a cloud of gas in front of a source of a continuous spectrum, you have a cloud of gas that's cooler than this. As the rays pass through this cloud, then whatever this is made up of is going to absorb. As the energy comes in, it's going to absorb and push electrons up to higher levels. Since it's absorbing that, then, and it's removing that at E equals HF, and when it's doing that, as it does that, it's going to be removing those lines from the continuous spectrum. Here's the continuous spectrum over here. As it goes through the cloud of gas, whatever this gas is made of, the energy is being absorbed at those specific frequencies. When it comes out to the other side, you can see that they're missing. They're gone. They have been absorbed. So right there in the word is what it is. A continuous spectrum, then, the continuous spectrum is hot and dense. The absorption spectrum you get from a cool, non-dense gas. And when we say cool, we mean cooler than what's behind it. It could be still to us very hot, but what we mean by this is that it's cooler than whatever is behind it. And then finally we get back to what we saw before, an emission line spectrum. That's where the gas itself is radiating. We saw where with a mercury vapor lamp, we're putting in electricity on either end. We're putting energy, and energy is being put in, and these electrons are then falling back down again. And as it gives that off, these waves are being given off in characteristic frequencies, E equals HF. And that's all we have, because it's coming out discretely. And so what you get is those lines themselves of this pattern of electrons falling back down again. And that's what we call an emission line spectrum, or a bright line spectrum. Bright line because you see these bright lines in the spectrum. It's it means the same. If you see bright line or emission, I prefer emission line because it tells me exactly where it's coming from. It's being emitted. And absorption line spectrum means they're being absorbed. It says here that the emission line spectrum is the inverse of the absorption spectrum. If you actually looked at this, if you looked at these colors here, you could take these colors and put them in here and you'd end up with a continuous spectrum. So it's just the opposite. So for the emission line spectrum then, the keywords that you're going to be looking for is hot, non-dense. And the density has to do with the fact that it's a gas. The molecules are further apart. Now that interaction is not filling in the gaps in between the lines, and so now you're having, what you're seeing predominantly is the electrons popping up and down and doing their thing, and that's all you're really seeing. Here's another slide. You know me, I like to have the same picture but in a different way of drawing it. So you have a hot body here, and if you put the light through there, it will give you a continuous spectrum. It's giving off hot white light. It goes through a cloud of cooler gas. Then the cooler gas is picking up the energy from the white light, and based on what this is made of, and you put that through the prism, and you can see the missing lines in the continuous spectrum. You see the missing lines, and this is characteristic of what this is made of. Or we can look at just the very hot gas. If it's very hot gas, we look at that, and it is emitting lines in those specific frequencies that tell us what it's made of. Now down here they have a representative of a spectrum we might see. Here's a continuous spectrum. Here's the absorption spectrum. I want to point this out. Here's the emission spectrum, and you can see that there's some colors in between here. There is some colors in between here. And if this gas were very hot but very non-dense, in other words, very thin, you wouldn't have this as much. You're going to see more black in some of this. But as this gets thicker and thicker, as it becomes more dense, as the gas gets more compact, you start having those intermolecular interactions. And so you start having these little energy bits being filled in. Now, as the gas gets thicker, thicker, and thicker, and it starts to become closer and closer, and the molecules are interacting more, it's going to become more and more like a continuous spectrum. Don't worry about it. For our purposes, we have these three: continuous spectrum, absorption line spectrum, and the emission line spectrum. But I want to point this out because we can use this. We can tell, based on how much it's filling in, we can tell how dense this gas is. What does this do for us? Well, we can look out there, and we can see gas pockets, and we can see large bits of gas. And if they're emitting, that means we can tell they're hot. We can see that they're hot, and they're emitting lines like this, put it through a spectrograph, we can tell what it's made of. We know what it's made of. And if it's relatively cool, there are stars behind it. And we might see an absorption line spectrum like this. It also tells us if there's a little bit of filling in there, we can tell how thick or thin, get an idea of how thick or thin this gas is. This is the sun spectrum. Now, you would think that if it's giving off light, why isn't it an emission line spectrum? And because it should just be radiating in these particular lines. It's an absorption line spectrum. I'll tell you in just a second. This is the sun spectrum. We've put the sun's light through a prism, and this is what we see. And all of these black lines here are being absorbed at certain specific frequencies. And we know exactly what those frequencies are and which element it belongs to. So in other words, we can look at this and see what the sun is made of, what's in there, and how much of it is there. It's mostly hydrogen and helium. It's mostly that, but it's got a smattering of a bunch of other stuff in there. The reason it's an absorption line spectrum, in other words, is being absorbed, what does that mean? I thought the sun was emitting. Remember, an absorption line spectrum you get from a cool non-dense. Well, the sun is hardly cool. What's happening here in the sun, we're going to talk about the structure of the sun later on. Here is the interior of the sun, and it's radiating lots of energy out from it. As it gets to the exterior, here's the outside. What we see, this is the light coming from the sun. What we see is the surface. We're looking at only the surface. So as this stuff comes out here, this is the sun gravitationally is very dense. It's very compact. And these molecules are interacting quite a bit so that you get a continuous spectrum. But as it goes through its outer layer of gas, this outer layer of gas is a lot cooler than this. Yes, it's very hot. I know. To us, it would be extremely hot. But it's much cooler than what's going on the inside of the sun. So as the continuous spectrum passes through this outer layer of gas, that's what we're seeing. The lines are being absorbed from whatever this is made of. So this is telling us what is in this outer layer of gas here. And that's why it's an absorption line spectrum. Even though it says, well, Mr. Todd, it's a cool, non-dense gas. Yes, this is much less dense than this, and it's much cooler, even though to our particular taste, it's very, very hot. All right, the next one then is Vene's law. I know it looks like Wien, but it's pronounced Veen. I used to call it Wien's law, or as another student called it, Wiener's law. It looks like Wien's law. I used to say that a couple of times until somebody corrected me and said it's Vene's law. I looked it up, and yes, it's pronounced Veen. Doesn't matter. Vene's law tells us a few things here. This is true of light in general. If anybody does any pottery or something like that, if you've ever made a clay pot and then put it in the kiln, this ought to tell you, you ought to know what you would see. Anyway, I'll get to that. Vene's law says that all bodies at temperatures radiate energy. They all radiate energy. the higher the temperature of that body, the more energy it gives off. So here we have one at 3,000 Kelvin. Remember, we did Kelvin in our lab, measured from absolute zero. Here's a body that's at 3,000 Kelvin. This is emitted energy. This is how much energy is being given off. This is wavelength here. And you can see that a 3,000 K body, it gives off this amount of energy, a certain amount of energy. By the way, it's all of this. You can see that this is all of the wavelengths. This is how much energy in that particular wavelength. So the energy is, you have to add up all of this. At 4,000 Kelvin, you can see that all of the energy underneath this curve here, all of that is more than the lower temperature. So the higher the temperature of the body, the more energy it gives off. And finally, at 5,000 here, you can see it's giving off quite a bit. So Vene's law says that, 1, all bodies emit energy. 2, the higher the temperature of the body, of the thing that's emitting, the higher the temperature, the greater the amount of energy, greater total energy. And then 3, you can see that there is a peak here. This is emitting, this is all the energy that it's emitting, but if you look at somewhere in here, it levels out, it tops off. It's the highest one. In other words, we could find a wavelength here that is the highest wavelength that it emits, meaning that most of the energy is in that particular wavelength. And conversely, most of that energy is at that particular frequency, right? We could use wavelength and frequency interchangeably because we can solve for one or the other using that equation. Here we see that this body here is at 4,000 K. Its peak emitting frequency or wavelength is up here in the red here. And then this one, it's even hotter. You can see that its peak frequency is at a higher frequency. So the third part of Vene's law is that the higher the temperature, the higher the, and I'm going to use peak frequency. Peak frequency. And we could put wavelength here because we could solve for one or the other. It means the lower the wavelength is getting shorter and shorter. So this body here that's emitting at 3,000 K, now that's pretty hot. And here it's emitting wavelengths in this invisible light here. So if we were to see this, it's pretty warm. And if we were to look at this, you can see that there's some in the blue, but there's a lot more in the red. This would appear to be a dull red to us. It would appear reddish color because you can see that there's more red coming out. This one at 4,000 K, yes, it's emitting in the red, and there's some other blue and the yellow and everything. This would appear to be orangish color. Orangish perhaps with some yellow. It's got some high and red. You mix those together. These would be washed out a bit. And then this one at 5,000 K, this would be mostly a yellowish color. You can see mostly yellow. It's got some reds. These are being washed out a bit, but it's mixing in. So this would be a whitish color. I mean a yellowish color. So in other words, what does Vene's law tell us? It tells us the conclusion is the higher the temperature, then the greater the peak frequency. And we can use this, I already wrote this once, but this is the summary of it. We can use this, we can look at stars. We can look at stars and look at their peak frequency. We can run a spectrograph and get this information. The highest frequency it's emitting, that immediately tells us what the temperature is. The temperature of an object is directly related to the frequency. You don't need this. You don't need this equation, but the frequency is directly related to the temperature. I think it's to the fourth. Doesn't matter. We don't need this. We're not going to do this part of it for our class, but knowing the frequency, we can tell what the temperature is. the peak frequency. So that's what it tells us. Here's another graph of the same thing. On this over here we have intensity, relative intensity. What was intensity again? It's the amount of power per square meter. We can break that down into the amount of energy per unit of time over a certain area. Don't worry about the area. It's how much energy, and the energy is coming from where? The rays themselves. So really we're counting up how many rays. In other words, this is a measure of how many of these light waves are there, is really what this is. So, and here is wavelength along here. And so for a human at 310K, we're emitting wavelength down here. You can see that we are not emitting invisible light. We're not giving off visible light. Well, how can I see you, Mr. Todd? Well, I've got reflected light coming from you. It's reflecting off of me. That's how you can see me. We're giving it off down here in the low infrared. Here is a 3,000 Kelvin star. It's a fairly cool one. This is probably a red dwarf or something. The peak emission frequency you can see here, peak wavelength here, which would also give us a frequency. In other words, most of the waves are at this wavelength, and this is in the infrared. This would be a fairly cool star. You can see here when we actually can see it. This is the visible light. You can see it. It would be probably a very dull red. This star here, the sun at 5,800K, this is our star, and it goes across here, and it appears to be yellowish when you mix these yellowish-white color. And then a 15,000K star, one that's very hot, would be emitting up here in the ultraviolet. Its peak is up in the ultraviolet. We look at the peak, we can find the temperature from that. And if we were to look at that star, you can see there's not as many red, and there's more blue and green. You mix those together, this star is going to appear bluish to us. So you can look at the stars and look at their colors and see if it's cool or very warm. The sun spectrum, this is same drawing, but this is for our sun. It seems to peak in roughly green, and the sensitivity of the human eye is, it peaks at the same place that peaks. Is that a coincidence? I don't know. It doesn't surprise me that life would develop an organ that would detect light waves at the peak frequency of the star that we are circling. So if there's life around a red dwarf, maybe they have an organ that can detect objects at that peak frequency. In other words, they would have an eye that could see infrared. And if there's a planet around a star that emits mostly in the more light waves in the ultraviolet, then they probably have eyes that can see in the